Hello, my name is Yusuf Chittalwala and I'm the Applications Engineering Manager for the Test and Measurement Instruments Group at Yokogawa Corporation of America. Today we are going to take a look at two methods of measuring current using a power analyzer. The first is the direct current input method, which makes use of the highly accurate shunt that's built inside the power analyzer. The second method uses voltage measured across an external shunt that is then applied to the external current sensor input of the power analyzer, which can then be scaled and make your current measurements. Now, depending on your application requirements, either of these two methods can be used. For applications where higher accuracy is of high importance, I would recommend using the direct input method. You may ask why? Well, several reasons. First, being that the shunts built inside the power analyzer are highly accurate and calibrated for both AC and DC signals. The accuracy of the current measurements made by the instrument is guaranteed based on the shunt's accuracy, which in turn also defines the accuracy of the power being measured by the device. There is no other device between the signal and the measuring instruments, therefore higher accuracy and precision are the natural outcomes. I mean, not to say that there are no other accurate external shunts available in the market. Of course there are. However, when you are using such an accurate power analyzer, why would you introduce a device in between and degrade the overall accuracy of your measurements? There are applications where using an external current sensor is imperative, but you do have a choice. You either use an external sensor which has a current output which can then be fed into the direct input terminal of the device, or you use an external current sensor that has a voltage output which can be applied to the external current sensor input of the device. But once again, for better accuracy and if your application permits it, you should evaluate a sensor with the current output. Now, the second reason why using a direct current input terminal is better, current signals are less susceptible to noise than voltage signals. So using the direct current input terminals of the power analyzer itself will minimize the effects of external noise on the signal and hence make better measurements. For all other applications where accuracy is of low importance, external current sensor inputs can always be used and are available. On the Yokogawa power analyzers, the direct current input terminals come standard. These are the two current knobs, the black current knobs that you see, and the external current sensor input are available as a separate option. The direct current input terminals can measure current up to plus or minus 50 amps RMS, depending on the model and the configuration. Well, the external current sensor input can measure voltage up to plus or minus 10 volts. Applications involving higher current measurements, Yokogawa offers a broad range of external current sensing systems which are matched and guaranteed with our power analyzers. The combination of these devices addresses a good portion of the industry's applications that involve testing, such as electric motors and drives, inverters, appliances, and other electronic products that require current measurements. Now, here are a few examples of current sensing devices that are offered by Yokogawa. Just a word of caution, never disconnect the current leads from the power analyzer while the current is flowing through them. This will damage the CT and could potentially be very hazardous to you and the testing environment. So, in summary, the two methods used to make current measurements are either the direct current input terminal or the external current sensor input method. If you are making current measurements and are in need for these accurate devices, please feel free to visit us at tmi.yokogawa.com for the best possible solutions. Yokogawa's complete line of power analyzers, from the WT310 to the high performance WT3000 are some of the most commonly used instruments in today's testing of power electronics. They are accurate, they are reliable, and they are easy to use.